On the pitch, it weighs just over 400 grams. But at the 2026 World Cup, this ball can influence a goal, an offside flag, and even the fate of an entire national team. From the outside, it is still the familiar ball everyone knows. But to make it, the factory must start with flat sheets of polyurethane, cut them into panels, create aerodynamic textures, print the graphics, integrate the sensor, seal everything with heat, and then test it under FIFA standards. Just one small deviation in roundness, weight, rebound, or air pressure is enough to keep the ball out of the match. Today, Factron Process takes you inside the manufacturing process of the World Cup match ball, where a seemingly familiar piece of sporting equipment can capture the attention of more than 5 billion viewers over 39 days. A country that has never played in a World Cup is the birthplace of nearly 70% of the soccer balls used around the world. That country is Pakistan, where the city of Sialkot has become the manufacturing center behind millions of balls used on pitches across the planet. Before they become symbols of each World Cup, many official match balls are first criticized for the way they feel, fly, or behave in the air. But their history goes back much further. From hand-stitched leather balls, to the black and white Telstar of 1970, and now to seamless designs with fewer panels, greater stability, and built-in sensor technology. So to understand why one small ball can spark controversy, become an icon, and appear in some of football's greatest moments, we have to begin where it is born. The journey of making the ball's bladder begins with synthetic rubber, usually butyl rubber, a material chosen because it can hold air far better than ordinary rubber. At first, it is nothing more than dense black blocks, with no resemblance to the ball that will one day roll across a World Cup pitch. The rubber is fed into an industrial mixing mill, along with additives that improve elasticity, durability, and resistance to air leakage. Inside the machine, heavy steel rollers rotate in opposite directions, continuously crushing, pressing, and stretching the material under heat. Workers may fold the rubber sheet and feed it back through the rollers several times, making sure every additive is evenly dispersed throughout the mixture. Once the rubber reaches the right level of flexibility and consistency, it is rolled into long, flat sheets only a few millimeters thick. The surface is coated with a fine layer of talc to prevent sticking, then wound into large rolls. From here, the material is ready to enter the mold and become the part that holds all the pressure inside the ball. A World Cup ball can only fly consistently when the bladder inside holds air pressure almost perfectly. That is why, after the rubber has been rolled into sheets, the factory begins shaping the bladder, the component that determines the ball's tension, rebound, and ability to hold its form. The rubber sheets are cut into blanks, then moved to a work table where the inflation valve is attached. Workers mark the exact valve position, punch a small, clean, round hole, then insert a firm rubber valve and secure it with specialized adhesive or light pressure. This is the most sensitive point of the bladder, because even the tiniest gap can cause the ball to lose pressure. Next, the rubber blanks are carefully aligned and placed inside a spherical metal mold. The hydraulic mold closes, applying heat and pressure at the same time. The rubber softens, bonds tightly along the seams, and forms a smooth, sealed air chamber. After cooling, the bladder is inflated and checked for air leaks. One simple but effective test is to submerge it in water. If even a small stream of bubbles appears, the product is rejected immediately. After the bladder is inflated and holds a stable shape, it is transferred to a multi-station thread winding machine. Here, the bladder is fixed onto a rotating shaft and spins continuously, while rollers and guiding arms keep it perfectly centered. From large spools, fine polyester or nylon threads are pulled out, passed through a tension control system, and then wound across the entire surface along pre-programmed paths. The machine must control the rotation speed, pulling force, and winding angle at the same time. So the thread layers are distributed evenly without sagging, tangling, or building up in one area. On average, a single bladder can be wrapped with hundreds of meters of thread in about 10 minutes, creating a hidden load-bearing frame beneath the outer cover. This inner frame helps the ball maintain its roundness, limits swelling and deformation, and keeps it more stable under powerful shots. After winding, the bladder is inflated again, coated with a thin layer of adhesive while still rotating, and sent through a drying area to prepare for bonding with the outer cover. How many meters of ultrafine thread do you think it takes to keep a ball from deforming after thousands of powerful shots? While the bladder is being inspected, another production line begins making the outer cover. The part that comes into direct contact with the player's boot, the grass, and the weather. Today, this outer layer is usually coated with polyurethane or synthetic PVC. Each roll of material is loaded into a calendaring machine and pulled through a system of large rollers. Adhesive is applied as a thin layer between the surfaces, then heat and pressure press the layers tightly together. The machine must maintain stable pressure across the entire width of the material roll. A good outer cover has to withstand constant friction, yet remain soft enough for players to control the ball. The multi-layered material roll is laid flat on the cutting table, where the ball begins to appear through each individual panel. To create precise cuts, the factory uses either a stamping machine or a laser cutter. The stamping mold delivers speed, separating many panels in a short amount of time, while the laser creates sharper edges and helps reduce material waste. Whichever method is used, every panel still has to be uniform, because even one slightly misaligned piece can make the ball's surface unbalanced after assembly. Once the pieces have reached their final shape, they are moved to the printing area. Here, logos, product codes, technical markings, and colored graphics are applied to the surface using specialized machines. In modern match balls, the graphics do more than create a striking appearance. They also help viewers recognize the ball's movement and spin direction on the pitch. After the panels have been cut and printed, they are still just flat pieces of material. They are moved to the assembly area where workers or positioning systems arrange each panel around the core, which includes the bladder and the reinforced thread layer. Every piece must sit in the correct position. The edges must line up evenly, the graphics must connect seamlessly, and the inflation valve must remain uncovered. Even a small misalignment can make the ball unbalanced after pressing. Once the alignment is complete, the back of each panel is coated with a heat-sensitive adhesive, ready for the thermal bonding process that will turn the separate pieces into one seamless outer shell. The major turning point in modern football came at the 2006 World Cup, when Team Geist replaced the traditional stitched structure with 14 thermally bonded panels. From that moment on, thermo-bonded technology gradually became the foundation of many modern match balls, helping create a smoother, tighter, and more stable surface. At this stage, the panels, already coated with heat-sensitive adhesive, are carefully arranged around the bladder and the reinforcing layers inside a spherical metal mold. Each piece must sit in the correct position, the edges must be evenly aligned, the graphics must connect in the right direction, and the valve must remain uncovered. When the mold closes, high heat and pressure soften the adhesive, seal the panel edges, and press the entire material structure tightly against the curve of the mold. After only a short cycle, the separate panels bond into one seamless surface without the need for stitching. Thanks to this structure, the ball has better water resistance, holds its round shape more consistently, and provides a more even contact surface during play. Once it is removed from the mold, workers clean away excess adhesive, inspect the seams, roundness, and printed surface before the ball moves on to pressure stabilization and performance testing. To meet FIFA standards, the ball is inflated to a specific pressure, then checked for weight, circumference, and dimensions from multiple directions. For a size 5 ball, the circumference usually ranges from 68 to 70 centimeters, and the weight from 410 to 450 grams. Roundness is measured with a CSM across multiple axes, because even one slightly swollen side can make the ball's flight unstable. Inside the testing room, the ball faces conditions far tougher than a real match. First comes the rebound test. A machine drops the ball from a fixed height, sensors measure how high it bounces back, and the process is repeated to see whether the response stays consistent. Then the ball is rotated across multiple axes to check its roundness, inflated, and monitored for pressure loss from the valve, panel edges, or bladder. After all of this, the ball must keep its circumference, roundness, pressure, and structure. Only those that pass every test move on to finishing, packaging, and export. The balls that pass every measurement and performance test are moved to the finishing area. Workers clean the surface and inspect the colors, logos, valve, and product code before sorting each ball by model and order. To save space, many balls have some of their air released before being packed into bags, boxes, or cartons. The cartons are counted, labeled, sealed, and moved into storage. From there, they are exported to stores, clubs, and stadiums around the world. The journey from raw materials now ends with thousands of identical balls ready to be inflated and sent into new matches.
Here, dozens of parallel strands are wrapped continuously onto rotating green spools, layer by layer, until each roll reaches its full size. Anywhere from a few kilograms to well over 10, depending on capacity. If the winding speed climbs too high, the strands overstretch and lose elasticity. Too slow, and they slacken, overlap, or tangle, causing breakage later during weaving. The machine maintains constant tension automatically, while operators stand by to monitor alignment, correct strand guidance, or replace spools once full. A clean roll with fibers packed flat, consistent, and aligned in one direction is visual proof of a well-tuned line. The more uniform the roll, the smoother the weaving process and the cleaner the turf surface will appear. From the rack, these hair-fine strands pass through alignment rollers, where they are grouped into straight rows and guided into the needle zone. This is where turf takes shape. Hundreds of needles move up and down like a giant sewing machine, hooking the fibers through the backing below, before pulling them back up to form standing. The backing typically consists of two bonded layers, a strong lower layer that carries tension, and a softer upper sheet for needle penetration. Right after weaving, the turf sheet is still not ready for use, because each fiber is held only by a mechanical loop. Grip strength at the contact point between fiber and backing is low, and a blade can still be pulled out by hand. To increase bonding strength, the sheet is sent through a latex coating system. Doctor blades and rollers spread the coating into a thin, even layer across the entire surface. The goal here is not thickness, but penetration, to seal and saturate the fiber roots. As it passes through the coating zone, the latex flows into the gaps, filling the space between every stitched loop and the backing surface. The adhesive then begins to stabilize, forming a film around the base of each fiber. Penetration and initial setting happen quickly, but bond strength continues to grow in the next stage, drying. The turf sheet then enters a heated curing chamber or continuous drying conveyor. At this point, the turf transitions from raw woven form into a fully bonded construction, mechanically stronger and ready for the next phase. Every punched hole must be clean, round, and smooth-edged. No burnt rims, no tearing. When the sheet exits this station, the underside displays a continuous, uniform grid of drainage holes, aligned even and ready to carry water down through the base layer under all weather conditions. This marks the end of the technical base treatment stage before the mat is flattened, rolled, and prepared for packaging. After perforation is complete, the turf moves into inspection. First, it is examined directly on the line, where operators scan the surface under strong lighting to catch defects quickly. Any questionable point is marked immediately for localized correction or removal from the roll. Once both visual inspection and lab performance pass specification, the turf advances to the final stages of production. After inspection, qualified turf sheets move into the flattening and pile setting zone, where rollers lift the blades back upright and remove any creases left from processing. Immediately afterward, the winding system pulls the mat onto a paper or PVC core. The roll reaches the required length, the machine cuts the sheet automatically, and the edge is secured with industrial tape to prevent separation. At this stage, the product is fully built, structurally bonded, drainable, and field ready. It is shipped out to school grounds, sports centers, residential fields, or professional stadiums, where it will be unrolled, seamed, and put into play. From the factory, turf rolls are transported to the site and laid directly onto the prepared base. The subsurface is typically fine stone or light concrete graded with slope for drainage, so rainwater flows downward through the perforation holes instead of pooling on the field. Each roll is unrolled along the planned layout and tensioned evenly to prevent rippling or blistering during use. Once aligned, the edges between adjacent rolls are trimmed, matched and bonded with specialized seam tape. The joint is pressed tightly with a roller so the seam remains invisible. The perimeter of the field is then pinned or screwed into the foundation, ensuring the turf does not shift under heavy impact. The final step before play is infill, adding rubber granules and silica sand if the field requires standard ball bounce. The infill is spread evenly by specialized applicators and brushed in so particles settle into the fiber base, keeping turf blades upright without collapsing during play. When the surface reaches uniform height and infill density, the field is ready for use.
And that brings our journey through the complete manufacturing process of a soccer ball to an end. From mixing the rubber, shaping the bladder, calendaring the material layers, to cutting, printing, assembling the panels, and testing performance, every stage depends on the precise coordination of materials, machinery, and manufacturing skill. If you found this process interesting, don't forget to hit like, share this video, and subscribe to keep exploring more impressive production lines with Factron Process.